mainly because we are talking about something very important, and I think it'll be kind of like review for some of you, but this is like such a good skill on the SAT. So yes, as always, thanks for your messages. So yesterday, I screwed up the derivation of the quadratic formula. Okay, sorry. I made, so Audie, I think, stuck with me at the end of the lecture, and we sort of went through and found where I went wrong. And it turned out I just didn't distribute something properly. So clearly, you know, we all make mistakes, and so you're not alone in the mistakes you're making on the homework and so on and so forth. Like I make mistakes all the time. So if you want to see like the correct derivation, I just did it at the end of the lecture. And in fact, I should have done this earlier, but let me find the YouTube link of the last maybe 5 minutes of the video. You'll see the correct derivation. It's actually a nice derivation. And if you want to show off to your friends, even in college, you know, whatever. I mean, if you want to be impressive, oops, that's my own voice. Here's the video. It's a nice little thing to show off. Thanks, Audie. Yeah, it looks like I'm about to. I just posted the same exact link. Okay, I'm getting a call from my grandmother. Okay, I'll have to call her back. This is crazy. You guys are more important than my grandmother. Okay. So, okay, without further ado, we can get started. So, okay, so today we're sort of going to talk about, okay, so I guess let's start with this. What we found that the solution to the quadratic equation is what? Can someone, besides like the people who were really participating yesterday, can someone tell me, someone who wrote it down or someone who remembers? Someone I haven't heard from in a while. I'll wait. Let's see. Robin, I haven't heard from you. Ascension, I haven't heard from you. Brianna, I don't think I've heard from you. Happy belated birthday. Hope it went well. Daniela, I haven't heard from you. Fiona, I want to hear from people. And this is
of b plus or minus square root of b squared, a minus 4ac divided by 2a.
That's exactly right. Yeah. So good. And what's your name? Sorry, I can't see your who's talking. So sorry. Who is it?
Ria.
Okay. Great. Thank you. And yes, you are very right. So minus b plus or minus. And I was using capital letters. It's more conventional to use lowercase letters. But I like using capital letters to remind you that these things are coefficients, that these are not variables, okay? B squared minus 4ac over 2. So we found that this always works, right? And even when you have imaginary solutions, this thing can give you those imaginary solutions. So if you don't know how to factor a quadratic, this always works. So in theory, we've covered the math. You know, we have covered the actual mathematical sort of theory behind quadratics. It's a vast subject, but we've covered sort of by finding this equation. This is everything you technically should know. But it turns out that there are many patterns in these quadratics. Okay, and there are easier ways than to just have to plug this in every single time. There are easier ways to factor quadratics, and it turns out that if you learn to look for these patterns, you'll start seeing them in nature, and you'll start seeing them in your textbooks, and it'll sort of help you with other subjects in addition to math. So like in physics, you know, you'll find that you'll just be able to factor things by sort of eyeball, okay? You'll develop some more intuition. So even though you sort of know this, there's more intuition to be developed by learning what we're going to talk about today. Now, can someone remind me what this is? This thing under the radical? What is it?
The
discriminant, yes. And what happens when it's greater than 0?
There's two solutions.
You have two solutions, and they're real solutions, right? Two real solutions. And what happens? Sorry, desk is. What happens when it's less than 0?
No solutions.
You have no solutions. And for the juniors, and I guess really for the seniors, good. Yeah, people are saying no solutions. For the seniors, this means that you have two imaginary solutions. So we're going to talk about complex numbers, I think, at the end of the course, and it's one of the most fascinating things in math. And there is some complex numbers on the SAT, so it's like good to know. But so for our sake, for 9th through 11th graders, that there is no solution to this. For the seniors who will start seeing complex numbers soon, like really being used, two imaginary solutions. And that's like of profound, like the use of complex numbers, it's not just some, we'll talk much more about it, but it's not just some made up thing. You know, we talk about imaginary numbers and how they're not real, but they're very like tangible. They're very useful in modeling things in nature. So anyway, that's sort of getting ahead of what we need to be talking about. So what happens when the discriminant equals 0?
It's one solution.
Very good. And Adi, I so appreciate you participating. I don't want to tell you not to because I like it a lot. But I do want people to start. I'm gonna start calling on people because I haven't heard from, like, there are people in this course who I still haven't heard from, and I appreciate everyone who has said stuff, but it'd be nice to hear from more people. Okay, so I might randomly call on people today, as I was in the beginning. So yeah, so this means exactly one solution. And I just want to take a few minutes before we get really into these methods of factoring. I want to take a few minutes to graph some quadratics for you. And I wasn't planning on doing this because sort of what we're going to talk about today is more important than graphing, but graphing is a great way to understand what's going on in a quadratic. So generally, if I were just to make an XY sort of plot of, say, y equals x squared, I would find that, you know, plotting these things, you can do it for yourself, but plotting these things gives you this shape. And we saw this, I mentioned this yesterday, but it's called a parabola, okay? And it's a very geometrically significant shape, okay? And it turns out that the parabola is super important. Anything that goes as x squared, so if you have some x squared, you know, square relationship, nature is filled with these things. Like there are all sorts of systems, okay? So a graphical understanding is really helpful. So what are the zeros? I guess here, we can just talk about the sort of ingredients of this y equals x squared. What is the y-intercept? Remember the form.
C.
Yeah, it's C. And so what is C here? If I were to write this in that form, what is C?
0.
0, right? Yeah, very good, because clearly there is no term in this equation here that goes as x to the 0. So C is therefore 0, right? Because there's an x to the 0 here, secretly. Okay, so C is 0. That means that the graph touches the y-axis, this is the y-axis, at the point x equals 0, at the point y equals 0. And that point happens to coincide. The reason I got confused there was that point happens to coincide with the x-intercept. And graphically, we see that. But if you wanted to really verify that, you would put in 0 here, you know, and you would verify. You'd say, oh, well, obviously, you know, that y equals 0 when x is 0. Alternatively, you can do what we did yesterday and put this, you know, in this. You could identify A, B, and C and put that into the quadratic formula, and you would find that the x-intercept is indeed 0. It's trivial. It's a trivial result. But you can see that. What is the discriminant here? If I were to do this, so C is 0. What is A? Look, what is A? If I were to match this with this general form. Let's see. John, are you there? What is A? I was looking, okay.
Is it 1?
Yes, A is 1, very good. And what is B? Look. Is there anything that goes as x to the 1 here? No. So what is b?
Zero.
B is 0. Very good. And so if I were to put all this into the discriminant, b squared minus 4ac, what do I get? B squared is 0 squared minus 4ac. Well, a is 1 and c is 0, so the discriminant is clearly 0. And we know that when the discriminant is 0, that we only have one solution. And indeed, look, the entire graph, it bounces off this one point, and that point is x is 0, and that's the only solution. And then it goes off in this direction for infinity. Right? Make sense? So this is the simplest case. And in fact, this is the parent function of parabolas. You might remember that we talked about the parent function of lines, right? And that was y equals x. Well, the parent function for parabolas is y equals x squared. And now we can use all the same tricks that we used with lines, right? The transformations and dilations and all that stuff. So if I asked you to graph y equals, I don't know, 1/2 x squared, we know that what does this 1/2 do? You know, in lines, it decreased your slope, right? So going from y equals x to y equals 1/2 x, we knew that this would do something like this. If this was y equals x, we knew that 1/2 x would be a little shallower, right? In this case, it's a very similar thing. Here we don't have the notion of slope, but we do have the notion of vertical stretching and vertical squeezing. And the 1/2 is a number that's less than 1, and therefore it squeezes or it shrinks the vertical height by a factor of 1/2. So it's going to look a little more squished vertically. And so this is just a graphic, but you can see that the zeros are the same. The solution is the same. So you understand sort of the reasoning. You don't have to you don't have to make a table for this junk. You don't have to do any of that. You can just look at the parent function y equals x squared and sort of make adjustments accordingly. How about something like y equals x squared plus 1? Well, I know that that's just the parent function shifted up 1 unit, right? Because that's what this plus 1 is, as we talked about in the linear case. And so here, I'll use different colors. Here's y is x squared. And y equals x squared is the same graph, just shifted up 1 unit. Sorry, this is a really bad graph, but this is 1 unit. So every point on the old graph got moved up a unit. Make sense? So you don't have to do any tables, you don't have to do any of that junk. Okay? Now, what happens, this is the last sort of aside on graphing, and then we'll move on. What happens if I had something like this, x squared minus 1? So compare it to this. Well, can anyone tell me what this will look like?
It shifts down 1.
Yeah, it shifts down 1, but look what happens. If I shift the graph down 1, how many solutions do I have?
2.
2. And does it make sense from the discriminant? What is b here? What is b?
0.
B is 0. What is a?
1.
What is c?
-1.
Very good. And so the discriminant is b squared minus 4ac, and that would be, can anyone tell me? 0 squared minus 4 times 1 times -1. And that's 4. And so 4 is a number that's greater than 0. And we know from what we talked about yesterday that when the discriminant is greater than 0, we have exactly 2 solutions. And lo and behold, 2 solutions. How about this case? How many solutions are in this graph? How many times does this graph cross the x-axis?
None.
None. And does it fit our understanding? What is the discriminant here? What is a?
1.
What is b?
0.
What is c?
1.
So the discriminant b squared minus 4ac is 0 minus 4, right? A times c is 1. And so this is less than 0. And we know that when the discriminant is less than 0, that we have no real solutions, okay? So this sort of fits. So someone privately asked me in the chat, what does it mean to graph the behavior of y as a function of x? That is a very profound question. That's like sort of what we've been doing all along. You know, we've been taking some function. This is a function, right? So it takes a bunch of x values and it spits out a bunch of y values. And the y, you know, the x-axis there are many ways to think about it. Like you can think of the x-axis as the independent variable and the y-axis as the dependent variable. You can think of the x-axis as the input, the y-axis as the output. They all basically mean the same thing. But so yeah, anyway, I mean, yeah, you're modeling the behavior of a function. So it's a very useful thing to do. Okay, yeah, sorry, that was a very general question that someone asked me privately in the chat. So, okay, so this is sort of the method of graphing. And I can't remember on the homework. I wrote the homework like in April. So I don't even remember what I asked of you on there. If there is graphing, this is sort of the approach I want you to use. Today, we're going to learn that you can factor this nicely, and you can find that the zeros, does anyone know what these zeros are, what these points are? Just off the top of your head.
1, 1.
1 and -1, yeah. So those of you who know what we're going to talk about today, you would know that this can be factored as the difference of squares, and that using the zero product property, this means that x plus 1 is 0 and x minus 1 is 0. So anyway, this is getting ahead of ourselves again, but yes, that's what these points correspond to. So anyway, there are various ways to graph things, but it's a great convenience to use the parent function y is x squared and make transformations on it. Okay, so let's look at some special cases to develop some intuition about quadratics. And so this is all about practice. So make sure you have a pen and paper today. Tomorrow is actually going to be exciting. Not that other days are not, but tomorrow is very much about you, okay? Because you will be doing a sort of activity, and you will be submitting the activity at the end of the class, and there will be sort of competition, okay, among the grade levels. So there will be a competition among the 9th graders, 10th graders, 11th graders, and 12th graders individually. But it's all going to be practicing this stuff. So today we're going to develop the theory and sort of get some intuition. So what is this thing? How, you know, if I apply the quadratic formula to something of this form, oh, look, there's a mistake here. There should be an X here. First of all, okay, this is bad. So I made this yesterday at night, and I must not have been totally with it. Okay, that's better. Okay, so if I applied the quadratic formula to this thing, what would my, first of all, is this of the form y is ax squared plus bx plus c? Yes, no, maybe.
No.
It isn't quite, but it sort of is, because see, you have a term that goes as x squared. You have a term that goes as x, and you have a term that goes as x to the 0. So in a sense, so you can immediately read off what a, b, and c are. You know, a is 1, big B is 2b, 2 little b, big C is b squared. So I could plug this into the quadratic formula. Okay, but it turns out that if I just sort of think about this and sort of play around with this, I can just realize that this is just this. So if I use the quadratic formula, I would find that, in fact, okay, you want to do it? Let's do it. I feel I don't want to leave people hanging. What are the solutions to this general form kind of thing? Well, minus b, we've already done the hard part of identifying the parts, right? So minus b, minus 2b, plus and minus the square root, b squared, that's 4b squared, 4 little b squared, minus 4ac. Well, 4ac is 4b squared, and over, what is it? Over 2a. So 2a is 2. And indeed, look, this is 0, right? 4b squared minus 4b squared is 0, so I'm left with 2b over 2. And what is that? That's negative b. And indeed, if I set the left-hand side equal to 0, that's what we do when we find solutions, right? We set y equal to 0. When I do that, using my guess, right? My guess here was correct, because if you set x here equal to negative b, well, that gives you minus b plus b, which is 0, and that satisfies this equation. So clearly my guess was correct, that this thing factors into x plus b whole squared. So what I did is I used the quadratic formula. This is the formulation we did yesterday, but then I just showed you that, look, I have been able to recognize this, and it's okay if you didn't recognize it, but I've been able to recognize some pattern in this. And that pattern is that this first term, x, plus this last term, b, right, the actual square root of those terms, if you square that entire thing, that gives you this. And indeed, if you wanted to verify, you could FOIL this out. So first, x squared, look, outer plus bx plus inner, bx plus last, b squared. So first of all, does everyone know what foiling is? Does anyone not know what foiling is? Or when I say FOIL, do people know what I mean? No,
Multiplying it
okay.
out.
So Robin, you don't know what foiling is. Okay, thank you for being honest. Okay, so well, we're going to have to take a detour. So sorry for people who found this to be a review. This is going to be a very short detour, okay? Generally, Robin, and anyone who doesn't know what foiling is, pay attention, because I'm only going to explain this once. I was hoping people would know this from, I don't know.
I said it this morning. Wording. I said it this morning.
Okay, if you have your microphone on, I can do this. Okay, I'm going to mute everyone. If you want to talk, yeah, okay. If you want to talk, you can unmute yourself. Okay, so if I wanted to multiply these two factors together, there's this thing you have to follow, there's this pattern you sort of have to follow. And it's analogous to distributing, right? We talked about the distributive property, how this is AB plus AC. This is what your first homework assignment was on. But here, now we have a sum of two terms. Multiply. So in a sense, this is the generalization of the distributive property. Okay, you get what I mean, right? Okay, so the way you do this, the easy way to remember is the word FOIL. And it means that you multiply the first term with the first term. So that would be A times A. And then you add that with the outer terms multiplied together. So A times B. And then you add that with the inner terms, CI, inner. That's B times A, which is the same thing as A times B. And you add that to the last term, L for last. That's B squared. And so, or B times B. So this is A squared. AB plus AB is 2AB. And then this is B squared. So this is what foiling is. So I'll just do one more example. So if I had this general kind of thing, AB times C plus D. A plus B times C plus D. How would I FOIL this? Well, first, right, FOIL. Sorry if this is review. I know this is ridiculously boring for some people. First plus outer, AD, inner, right, I for inner, BC plus last, BD. So, okay, so this is all I'm going to say about this. So, Robin, does this make sense? Robin, you might have to unmute yourself because I muted everyone. Okay, we've lost her. Maybe I shouldn't have muted everyone.
His mic doesn't work.
Okay, I see. Okay. Well, I hope it makes sense. We don't really have time to, sorry, but I was hoping people would sort of know this. Okay, you were getting it. Good, thanks. Okay, and thanks for being honest. Okay, I appreciate it. So whenever you have something of this form, you know that it will factor into a perfect square. This is called a perfect square because you literally just take the first thing, square root of the first term, and you add it to the square root of the last term, and you square the entire thing together. So this case is very similar. What's different between this and this? There's only one thing that's different.
The second one.
Minus sign.
This minus sign. And so does anyone know sort of how this will affect the factoring?
It'll be a
negative.
Yeah, it's just this. So this is actually the same case as this, right? But you can just think of B being negative or alternatively X being negative. And if you want to verify that this is true, you can FOIL this out and you'll get precisely this. So this is called, these are both called perfect squares, okay? And you should, as soon as you see something of this form, you should immediately write that. And as soon as you see something of this form, you should immediately write that. They should be like, you don't have to technically memorize things for the SAT, but this is like an essential skill. This is more than memorization. This should be like in your blood. Okay, and then there's one last special sort of case worth knowing, and it's called the difference of squares. So how does this compare to this form?
It doesn't have a b.
Very good. Yeah, so b here is 0, but c is a squared, is negative a squared, and a is 1, right? So you could again put this in the quadratic formula, and you would find that the solutions are a and negative a. And how would I just do that without using the quadratic formula? So put this in the quadratic formula, and that's what you get. How would I know otherwise? Well, from experience, I know that if instead of factoring something as, the difference of something all squared, I can factor this as, one thing, the sum of those two things, times the difference of those two things. And if I FOIL this out, just from experience, foiling this out, I know, look, plus ax minus a squared. And these two inner terms, the cross terms, cancel. And so you're left with this. So I know this from experience, and I think many of you know this. So this is kind of review for people. But for those who are new to factoring, you should know these three cases like off the top of your head. So write this like 100 times, do whatever it takes. Get this in your blood. I thought that people learned this in 8th grade. That's when I learned it, 7th, 8th grade. But does anyone have any questions about these three cases? No, I assume not. Okay. So it's all about practice. Okay. So look, I'm gonna, for the sake of clarity, I'm gonna label these three cases because we're gonna do kind of examples based on these things. So call this case 1, okay, for which this is the factorization. Call this case 2, and call this one case 3. The difference of squares is case 3. So everyone have that sort of template? Okay. Which case does this fall into?
Case 1.
Case 1. And how would I factor it? Remember, if you're given this, which is what case 1 says, how would I factor this? What is 2b? First of all, okay.
8.
2b is 8. Look, 2b is the coefficient on x. 8 is the coefficient on x. Therefore, 8 is 2b. What is...
16 is 4 squared.
So b squared here is 16. So this is kind of redundant information because these things tell you the same thing, almost, but actually you need these two equations to tell you what b is. So from this equation, you get that b is 4. Okay. So if b is 4, then how does this factor?
X plus 4 squared.
Yeah. Look, I'm literally just, this is not intelligent. There is no intelligence in doing this. I'm literally just monkey see, monkey do. This is the intelligent part, right? Discovering how this thing factors. This is literally just regurgitation. That's what the SAT is about, unfortunately. That's why I don't want this course to be like, how to do well on the SAT. This is more, math is more than just what we're doing here. This is the math. So anyway, that's right. And so if this is the correct factoring, what would the solutions, first of all, what is the point of factoring? The point of factoring is to find solutions. And so how would I find solutions based on this equation?
You would FOIL.
No, I wouldn't FOIL because FOILing would give me.
Oh, yeah.
So how would I find the solutions? What is the solution? A solution is
Set it equal to 0.
Yeah, the solution is the x-intercept, right, of a
So
graph.
set y equal to 0.
And yeah, so I would set the y, equal to 0. So look, y equals 0. And then this is very easy to deal with, right? This equation is very easy to solve for x, whereas this equation is very hard to solve for x. You'd have to use basically the quadratic formula to do it explicitly. But because we recognize this pattern, we can immediately write this. And this really means this, right? This is the definition of the square, something times itself. And using the zero product property, I know that generally if two things like a, b equal 0, that either a equals 0 or b equals 0. And so using that same reasoning here, I would have the statement, x plus 4 is 0, that's my a. And the same statement for b, right? X plus 4 is 0. So these are kind of redundant statements. So you only need one of them in this case.
For this problem, couldn't you just get like the factors, like you could do like that x thing and then put like 16 on one side and then 8 on the other?
So we're going to talk all about that. I just want to go through some of the special cases first.
Okay.
Because these are sort of the ones that, actually all these cases that we're talking about have the discriminant. Cases 1 and 2 have the discriminant equal to 0. And that's really what the underlying specialness of these are. Case 3 has a positive discriminant always. And that discriminant is a rational. So sorry, I'm talking sort of abstractly, but case 3, Adi, has a rational discriminant. In other words, you can find the square root, and that square root is an integer or a number. That can be written as a ratio of two numbers. So anyway, kind of getting ahead of, but these are the special cases, so they're worth working through. But we'll get to your sort of trick later. Okay, so what case is this? Case 1, 2, or 3?
1.
Case 1. No,
that's 2.
Case 2 because of the minus.
Negative.
Yeah. First of all, with this example, I didn't finish it really. The solution to this equation is x is minus 4. Sorry, I got ahead of myself. And that matches, if you put in minus 4 into this equation, you'll get 0, right? You put in minus 4 for x, that gives you y is 0. So it's indeed a solution. Okay, so this is case 2, and I'm going to write case 2. Y is...
So it's the same thing, but it's x minus 4 squared.
Yeah. So if this thing, we just discovered that this thing factors like this. So what is b here? Well, first of all, what is negative 8?
2b.
Negative 2b. Yeah, watch out for the sign. So this means that 8 is 2b, which means that b is 4, right?
Yeah.
And because it's of this form, I can just put that into this little template that way.
Okay.
And indeed, this thing factors as such. Right? I'm literally just copying and pasting. I identified what b is, and then here it is. Okay, so what are the solutions? If I set this equal to 0, by inspection, you know that x is 4, right? You don't even have to use the zero product property on jump. You can just say x is 4. Right? If you put in 4 here, you would get 0. So I'm going kind of fast with the nitpicky little algebra, the sort of fine algebra details, because I assume that people can solve this kind of equation. I want you to get competent at going from here to here. Going from here to here is a piece of cake. Here to here is the real important part. Which does this fall into? Case 1, 2, or 3?
3.
3. Yeah, I was about to zoom out and go back. I guess you'll remember. So this is case 3. And case 3 said that...
Difference of squares.
Yeah. There you go. When you have something of this form, sorry, x squared minus a squared, that this thing factors into this. X plus a times x minus a. And so what is a here? Look, first of all, what is a squared?
It would be 4 squared, which is 16.
Yep. So a is 4, as you suggested. And so this would immediately, just using the template, monkey see, monkey do, this factors into what?
X plus 4.
And yep. And so what are my solutions?
4, negative 4?
Yes, very good. Yeah, because here, using the zero product property, you would have these two statements. And the solutions, the solution to this one is that x is negative 4. The solution to this one is x is 4. So if I were to graph this is a good one to graph. x squared minus 16. Okay, y is x squared minus 16, right? If I wanted to graph this, I could either think of the parent function, y is x squared, shifted down 16 units, or I could think of, oh, look, this is a quadratic, and the solutions are -4 and 4, so I'm going to put dots there. And I know that it sort of looks like y equals x squared, but I also know that what is the y-intercept?
-16.
Yeah, that's in this form, y is ax squared plus bx plus c. That's my c. That's my x-intercept. So I can draw a -16 down here, right? I'm going to mute everyone again because I hear. Okay. So if you're in a noisy environment, just please be considerate. Okay, so this is what the graph would look like. Does it make sense? How we sort of use the different cases? Let's do a few more. I have a feeling that this doesn't make sense to people. Because it's sort of, I don't know. Does anyone have any questions about these three that we just did?
Oh, for the third one,
Uh-huh.
what if it was y equals x squared plus a number? Would that be like no solutions?
Plus, very good. Yeah, very good. So it turns out that generally, pick your favorite number, whoever's talking.
16.
Plus 16. Okay. It turns out that anything of this form, where this number is positive, if this number is greater than 0, anything of this form has a negative discriminant. And when you have a negative discriminant, you have no real solutions. And graphically, it makes sense because, this is just the parent function, y is x squared, moved up 16 units. So here I moved it down 16 units, but, I can move it up 16 units way up here. And you can see that clearly this graph will never cross the x-axis. And therefore, it has no solution, right? So this is the point 16. This is the lowest the graph ever gets. But to have a solution, you need to cross the x-axis, right? So this is the sort of graphical interpretation of a negative discriminant. Make sense?
Yeah.
Very good. That's a very good question. And in college, I'm sure you will find this to be a fascinating case because it turns out that so much of nature, waves, basically, all waves can be written not quite in this form, but using a similar sort of idea, and waves construct reality. So anyway, that's way ahead of sort of where we need to go. But this is very profound. Both of these cases, this idea of the discriminant is like it's going to stick with you for years. Okay, how about the case 1, 2, or 3?
2.
Is it 2? So 2 had a minus sign.
1.
Yeah. And how would I factor this?
Divide 10 by 2 and then take the square root of 25.
Yeah, exactly. Yeah. So I'm not going to walk through all the different cases at this point. I think most people are comfortable with this now. So I know, yeah. So this is how this thing factors. And if you were to verify, so first of all, if you're confused, the way we got this is using the general form of case 1, which was x squared plus 2a plus 2bx plus b squared. And I said earlier that this factors as such. And so I identified, whoever just said that, sorry, I can't see your name, I don't know who's talking, but whoever said that, I basically identified that 10 is equal to 2b and that 5 is equal to b. And then she just put that 5 into this form, and that's exactly how we got that. And so what would the solutions be? If I set this equal to 0.
X equals -5.
And yeah, that's right. That's exactly right. And so if you were to write this way, you could then apply the zero product property, but that's not really necessary. By inspection, you can see that the only number x can be to satisfy this equation here is x is -5. So that is your only solution. And if I wanted to graph this, how would it look? If I wanted to graph this equation? Well, I know that the y, sorry, first of all, what is the y-intercept? I circled it. Anyone?
25.
25, and it's way up here. What is the x-intercept? Well, we just found it. -5 is way over here. So I have 2 points, and I can already I know that this is the only solution. So I know that the graph bounces off this point. And I know it comes back up here. So this is sort of what the graph looks like. Now you can also see, and we're going to talk much more about this form of transformations. And you will find that you can think of this as the parent function shifted to the left 5 units. That's all this is. We're going to talk about this much more in a few weeks. So if this doesn't make sense yet to you, it's all right. But you can graph this there are many ways to graph things and sort of to think about things. If you're ever in doubt, you can always just write a table and plug in numbers. That's the least efficient way. This way kind of combines forms. So we found the y-intercept from this form. We found the x-intercept from this form, from solving this equation, right? For y is 0. So anyway, so you people should be somewhat familiar with how to graph an equation like this. Any questions?
No.
Yeah.
No. Okay. So someone very kindly texted me and said you can click on participants and Alt U. Okay. I didn't know it. Okay. I'm not sure if that'll work, but okay. Thanks for whoever texted me. Okay. What about this form? Case 1, 2, or 3?
That would be 2.
Case 2, and I think I've done enough examples of how to match it to the individual case. So can someone just immediately read off how the factorization is?
X minus 6 squared.
What would you say?
Minus
6
6.
squared.
6 squared. Very good. I don't really know what else to say here for people who don't know how to get from here to here. Okay. Follow the templates of cases 1, 2, and 3, and it should be very self-explanatory. Okay, so what are the solutions?
X is 6.
Yeah, so if I set this equal to 0, this is clearly the only solution. And this would look like, graphically, a parabola shifted to the right 6 units. If you don't like this interpretation, you can look at the y-intercept, plot that, 36, so you know it's way up there somewhere. And then look at the x-intercept, 6, and then you can just kind of fit a parabola to those 2 points. Okay? So now there's some, okay, so so we've sort of looked at these special cases. Let's just do one more. This is case, which case? 1, 2, or 3?
3.
3, and how would it factor?
X
minus 9, x plus 9.
Yes, x plus 9. It's a difference of squares, and the solutions are x is 9 and -9. And graphically, I could put these, so I know that the x-intercept is way down here, -81, not to scale. And the y-intercepts are here, 9. Sorry, I said that wrong. The y-intercept is -81, right? The x-intercepts are given by here, these two, 9 and -9. And if I were to fit a parabola to these things, I guess something like that. Okay, so you sort of are seeing the picture here. Now, there are some, instead of just looking at this and like matching it to case 1, 2, and 3, there's actually a little trick that sometimes can work better. You'll notice that, so case 1 and 2, the discriminant was always 0, right? And in case 3, so here, discriminant b squared minus 4ac was 0. If you go back through this lecture and you look at all those examples we did, like this one, literally. Look, the discriminant here is 0. If you put in a, b, and c, you'll find that b squared minus 4ac is 0. And case 3 had a discriminant that that was the square of an integer, actually. So it was sort of, these were all very like procured sort of cases, very procured questions. But it turns out the discriminant can be positive too, right? And that will give you generally two different solutions. It doesn't have to be the square of like an integer, right? So like in this case, we had the solutions x is 9 and negative 9. We can have two different numbers, like two, we could have, we can have equations where solutions are like totally different, like pi and 4 pi or something. You can have different numbers that are have more difference between them than just a sign. So what I'm saying is that these are special cases, and they're really great to know because you can immediately sort of identify these types of questions and just write the factorization. But there are there are sort of tricks, and I think many of you have learned some of these tricks. I'm going to present one that I learned, and I think pretty simple, okay? So if you have your own ways of doing these things, you can tune out. You don't have to listen to kind of what I'm going to say. But this is a very useful trick, and let's use this as an example. So because we know what it factors into. X squared minus 12x plus 36. So this trick involves writing the factors of the first and the last term. So what are the factors? What are the two numbers that multiply to x squared?
X and X.
X and X. These are the two. I'll use a different color to show you that what I'm about to do is sort of not mathematical, it's sort of mechanical, okay? What are two numbers that multiply to 36? There are several choices.
6 and 6.
6 and 6 is a very good choice, but how about negative 6 and negative 6? Doesn't that also work? How about 9? How about 9 and 4? How about 12 and 3? You see the sort of ambiguity?
Mm-hmm.
So this is sort of the hard part, choosing which set of factors to express this as. It turns out that negative 6 and negative 6 is the choice you want. And the way I know that is because this is the very mechanical, non-mathematical thing, okay? The way I know that is that if I take this number, x, and I multiply it by this bottom number, so this times this, and I add that to this bottom number times this top number, this times this. So basically, if I add this product to this product, what do I get? I get the middle term. So this is sort of the pattern you should be looking for. And then I can immediately read off the factorization. And it is that x minus 6 times x minus 6 is equal to x squared minus 12x plus 36. So I know this is sort of a lot if you're seeing this for the first time. If you have your own ways of factoring things quickly, go for it. Do it your way. I think we all learned this differently. Yeah, so you'd immediately write off the answer. Okay, let's do it for another one. Like 10. Let's do it for this one. This computer is so slow. I don't know where I even am. They took me to the other side of the page. Y is x squared plus 10 plus 25. Let's just use that. Plus 10x plus 25. What two numbers multiply to x squared? There's only one choice.
X.
X and X. I'll use a different color. And what two numbers multiply to 25? There are some choices that are better than others. What two numbers?
5.
5 and 5 is the good choice. You could also pick negative 5 and negative 5, or 25 and 1, or 1 and 25, right? But 5 and 5 is the good choice because x times 5 is 5x, And when you add that to this, x times 5, I get the middle term, 10x. See? So I can immediately read off the factorization. Look, x plus 5 times x plus 5. Are people seeing the pattern? So now let's apply it to, let's see, I'll cook up a little example here. Let's apply it to something that doesn't, that has a discriminant that is not so procured. Okay, let's apply it to, let's see here. I'm coming up with something, give me a sec. Let's apply it to something like this. Sorry, let's apply it to this. So this case, it doesn't match case 1, 2, or 3. If you look through our examples, this does not fall under 1, 2, or 3. So it turns out that we're going to have to either use the quadratic formula or guess some solutions. And this method that I just showed you works great. And let's do it. What two numbers multiply to x squared?
X.
What two numbers multiply to negative 2?
2 and negative 1.
Yeah, very good. And you picked the right pair. We could have picked negative 2 and 1, but this doesn't give you, okay, we'll actually do it both ways. I'll do it the right way first, and I'll show you what happens if you use the wrong way. Okay, so look, we know that this is correct. We know that this is the correct choice for the way to factor 2 because x times negative 1 is negative x. And when I add that to x times 2, which is 2x, I get x, which is indeed the middle term. And so I can immediately factorize this as x plus 2 times x minus 1. And this is y. If I had picked the other choice, I would get the wrong factorization. And this is what would have happened. If I picked, okay, I'll rewrite sort of the problem. Okay, so if I picked negative 2 and 1, look, x times 1 is x, but when I add that to x times negative 2, that gives me negative x, which does not match this middle term. And if I tried to factor it this way, this factorization would not give me, if I foiled this out, this would not give me what I started with. So this is not the right approach. This is not equal to this. Make sense? Okay. Great. So let's try these. Oh, wait, so by the way, because tomorrow is very like you doing work yourself, there is no quiz today. I want to get through sort of the methodology today. I want to let it sit in your mind and let it brew, work on the homework a bit. Tomorrow, be ready to go, okay? Because there will be a nice activity. Check your email tomorrow morning around this time, okay? Okay, so how would I apply that method to this? What two numbers multiply to x squared? It's the easy part, right? X and x. What two numbers multiply to 2 and 1? There's only one choice. So sorry, well, I said the answer. What two numbers multiply to 2?
1
Mm.
and 1.
2 and 1, yeah, as I said. And indeed, look, x times 1 plus x times 2, that's x plus 2x, and that gives me 3x, which is exactly this middle term. So what is the factorization? Someone tell me, using what we found here.
X plus 2 and x plus 1.
Very good. Yeah, because it just goes across like this. X plus 2 times x plus 1. Okay, and using, you know, I could, if I wanted to find the solution, say, from this, what would I do? I would set this thing equal to 0. And using the zero product property now, what would I find the solutions to be, or the x intersects?
Negative 2 and negative
1.
Yes, and negative 2 and negative 1. The reason I found that was using the same reasoning, that if a, b, any two numbers a, b is 0, that either a is 0 or b is 0. And so these are, you know, you can say x plus 2 is 0 and x plus 1 is 0. And then solving these linear equations, you find these solutions. And if I wanted to graph this, what would I do? What is the y-intercept? Hello?
2,
And what are the x-intercepts?
-2, and negative.
Yeah, exactly what we found. And look,
Sounds-
negative 1 and -2. So you can now see that this graph kind of looks like this. Yeah? So you can see that this is a more general graph. Remember our other graphs, they all had like only one solution, and they were sort of like all displaced like this, or they were all displaced like this, remember? Like vertically displaced.
Mm-hmm.
But do you see now that this is a combination of a vertical and horizontal displacement? See, it's like moved to the left some, but it's also moved down some. Does everyone see what I'm saying? How this, visually, this is a more general case than what we were talking about earlier. The reason being that this is not case 1, 2, or 3. Does that make sense?
Mhm.
Great. So, does anyone have any questions, first of all, about this example? Let's just do one more in the few minutes we have left. What two numbers multiply to x?
3 and 4.
X and X.
3 and 4 multiply to x.
3 and 4?
I'm
Okay.
dumb.
You're talking about the 12, yeah. So 3 and 4 multiply to 12. And I know that, you could also pick 6 and 2 and 2 and 6, and these are the same, or 12 and 1. But none of these cases are good because I know that if I multiply, why is this so slow? If I multiply this times this, and I add that to this times this, I get 7x. Indeed, 4x plus 3x is 7x. And so someone tell me what the solutions are. Tell me what the factorization is, and then we'll talk about solutions.
X plus 3 and x plus 4.
Very good. And now what are the solutions?
-3 and -4.
Very good. Using the zero product property. I think many of you are catching on very well. If you're still confused, please attend the office hours today. They're at 1 p.m. Okay. Patricia is just amazing. I'm very grateful that we have her help. She's been really good. If you're confused, please go. So what would the graph look like? What are the
It would be to the left, to the right 3, and then up, down. Sorry, there's no Y. I'm not looking at the right.
It's okay. So that these give you, I would probably plot the x-intercept, the y-intercept first. So this is where the graph touches the y-axis, and then I can also plot these points, -3 and -4, and they're kind of close to each other. And so I know that the graph will look something like this. If I try to fit a parabola to these things, there's only one way to really do it. And you can again see that this is a more general case because it's a combination of vertical and horizontal displacement. Make sense?
Yeah.
Yeah, so it doesn't lie just like case 1, 2, and 3. All of those graphs, either case 1 and 2, they all look like this, one side of the, and in case 3, all of the graphs were like this. In fact, case 3 didn't include these guys because these, yeah. But case 3 looked like these, right? So you can see that this is a combination of sort of cases. Okay, it's 11:01. I'm going to do one more. Okay. What two factors?
X and X.
Yep. What two factors?
4 and -3.
Very good. Yeah. So, yeah, I know that this is like ridiculous review for a lot of you. So thanks for your patience. I hope that I'm not going too fast for people who have not seen this before. So I know, yeah, so this times this, -3x plus 4x is x, and that matches this. So we know that this choice is correct. And the factorization is x plus 4 times x minus 3. And if I were to find the solutions, then I'd set this to 0. And I'd find that the solutions are these. And if I were to graph that, you can see how it's not symmetric about either the x or y axis, like cases 1, 2, and 3, and how I'd have -4, 3, and -12 as the y-intercept, and how this sort of looks like that. Yep. I've been putting arrows on my graphs as a habit from middle school, and high school, but you don't have to put arrows on your graphs. No one in the real world does that. You can just draw the lines. Okay, so that's really it. I mean,
I
we
have a
can keep
question.
going. Go ahead. Yeah, go ahead.
On
Free to
the
leave it
ACT
here.
or ACT, are they allowed to have calculators?
I have no idea. I have no earthly idea. And that's a question that you could probably find the answer to online. I really don't know about the ACT. I honestly don't even know like the rules to the SAT anymore because the test has changed so much. All I did in preparation for teaching this course was I looked at sort of the like syllabus, so to speak, like the sort of course content. Okay, so Adia has nicely said you can use the calculator for SAT on section 4 and not section 3. Okay, so that's in for, yeah, that's great to know. I have no idea. I'm just teaching the math. Aruhi asked, is there an attendance quiz? No, there is no attendance quiz today. Tomorrow is like a big sort of day where you'll be participating a lot. So I decided to forego the attendance quiz. Okay, I'm gonna stop recording.